Hello everyone. Today I'm going to start Unit 5, that is Laplace transform. So Laplace transform is a powerful tool in diverse field of engineering. This Laplace transform is used for solving linear differential equations with given initial values of an unknown function and its derivatives without the necessity of first finding general solution in the sense in the previous differential equations we used to find complementary function and particular integral. So without the necessity of finding complementary function and particular integral, we can evaluate linear differential equations with initial values, and then evaluating from it the particular integral solution satisfies the given conditions. This technique is useful to solve some partial differential equations also. So let us write the definition of Laplace transform. Let f of t be a function defined for all positive values of t, comma, then the Laplace transform of f of t denoted by Laplace of f of t, that is L of f of t, or f bar s is defined by Laplace of f of t is equal to f bar s is equal to integral 0 to infinity e power minus st f of t dt. So this is equation 1. Here from the definition it is clear that a function of t is given, then the Laplace transform of f of t denoted by Laplace of f of t is equal to f bar s. When you apply Laplace to the function of t, then you get a function in terms of s, which is denoted by f bar s, and the formula for applying Laplace for the function of t is integral 0 to infinity e power minus st f of t dt. So we take this as equation 1, provided that the integral exists. Hence here the parameter s is a real or complex number. Okay, then the relation 1 can also be written as f of t is equal to L inverse f bar s. So this is nothing but inverse Laplace. Now in such a case, the function f of t is said to be inverse Laplace transform of f bar s. The symbol L, which transform f of t into f bar s, can be called the Laplace transform operator. Then the symbol L inverse, which transforms f bar s to f of t, can be called the inverse Laplace transform operator. Here from this it is clear that whatever terms we are taking here in Laplace transform, in defining Laplace transform, I have written here clearly. Once if you go through that, here we are saying that this is the definition of Laplace transform. In this, s is nothing but a real or complex number. The relation 1, this is can also be written as f of t is equal to L inverse f bar s. This is nothing but inverse Laplace transform. Here we write the function f of t is said to be inverse Laplace transform of f bar s. The symbol capital L, which transform f of t. Just now I have told you, whatever function f of t we have, that we are transforming into f bar s. That is, function of t is transformed to f bar s, can be called as Laplace transform operator. The symbol L inverse, which transform f bar s to f of t, can be called as inverse Laplace transform. So this is about the definition of Laplace transform. Now we'll take next topic, that is nothing but sufficient conditions for the existence of the Laplace transform of a function. So in the next topic we will discuss the conditions in order to solve when a problem is given in terms of Laplace transform. Now let us write the topic. So that is nothing but sufficient conditions for the existence of the Laplace transform of a function. Sufficient condition for the existence of the Laplace transform of a function. Now let us write what is given here. So here, while finding the Laplace transform, transforms of elementary function comma, it can be noticed that the integral exists under certain conditions such as s greater than 0 or s greater than a, etc. Next line. In general, comma, the function f of t must satisfy the following conditions for the existence of the Laplace transform. Now here there are two conditions in which the function f of t must satisfy for the existence of Laplace transform. Number one, the function f of t must be piecewise continuous or sectionally continuous in any limited interval 0 less than a less than or equal to t less than or equal to b. So first let us write the conditions, and then when the problem comes I'll show you the examples based on this. So when you say the problem, when a problem is given, it is a sectionally continuous or piecewise continuous, and second condition is the function f of t is of exponential order. So how will be the problem to find in terms of Laplace transform? The problem will be in terms of piecewise continuous or sectionally continuous in the interval 0 less than a less than or equal to t less than or equal to b. And second condition should be the function f of t is of exponential order. So the problem will be in these two conditions. Okay, so then only we can solve the problems. Now I want to explain what is a piecewise continuous function. So let us make you clear what is piecewise continuous. So let us write this piecewise continuous, and then I'll give you the examples based on this piecewise continuous function. When you say it is piecewise continuous, when you say a function is a piecewise continuous, so here we write a function f of t is said to be piecewise, or in bracket sectionally continuous over the closed interval a comma b. You know that what is closed interval and open interval. When you have a closed interval, whatever values we have inside a and b should be included. When you have open interval, we exclude a comma b there. So in the over the closed interval a comma b, if it is defined on that interval and is such that the interval can be divided into a finite number of subintervals comma in each of which f of t is continuous and has both right and left hand limits at every endpoint of the subinterval. So this is the definition of piecewise continuous. So once I read the piecewise continuous definition, a function f of t is said to be piecewise or sectionally continuous over the closed interval a comma b if it is defined on that interval and is such that the interval can be divided into finite number of subintervals, in each of which f of t is continuous and has both right and left hand limits at every endpoint of the subinterval. So I'll give you the example how we will take. So for example, in the previous classes we have learned, once we have seen that when an interval is given, like from 0 to infinity, we have taken the integrals from 0 to 1 plus integrals 1 to infinity. In that way, there are nothing but endpoints. What are the endpoints here? 0 to 1 and 1 to infinity. That are nothing but subintervals. So in that way, we take piecewise continuous. Let me show you the example based on piecewise continuous. So why we are studying about piecewise and exponential order? The problem should be in the form of piecewise continuous as well as in form of exponential order. Then only we can do the problem based on Laplace transform. So now let us have an example based on piecewise continuous. So example 1. If I give you the the function f of t is equal to t square comma 0 less than t less than 5. Another here we have to write a function 2t plus 3 comma t is greater than 5. So you can see here this is a function which is called as piecewise or sectionally continuous for t greater than 0. That means here whatever the limits are given, that limits are t for t greater than 0. Now this is the function. This function is said to be piecewise or sectionally continuous. Let us have second example. The function f of t is equal to 1 upon t is not sectionally continuous in any interval containing t equal to 0. Okay, so this is nothing but here I have given you. So whenever a function is given, a function of t is given, if you want to check whether it is piecewise continuous or sectionally continuous, then this example will be helpful for you. So piecewise continuous function will be in this form. So this is not a piecewise continuous. Here only a function is given, and in any interval is not an sectionally continuous in any interval containing t equal to 0. Here when you substitute t equal to 0 here, it becomes infinity. Now second is we have functions of exponential order. Now here let us the function f of t is said to be of exponential order a if limit t tends to infinity e power minus at f of t is equal to, we get a finite quantity. Here when a function f of t is given, then when you apply the limit for the function f of t, then we will get a finite quantity. This is the definition of functions of exponential order. Okay, so let us we will do problems based on these two conditions in coming now. So let us have, after this we will have general property. I'll make you to understand I'll give you examples in terms of problems. After completing the first, we will complete general property, and then we'll write Laplace transform of elementary functions, and then when we are doing problems based on that, I'll show you the examples of these two conditions. Now general properties. Of Laplace transform. In this, let us study about linearity property. First, linearity property. So in this linearity property, let us study what it is. So here we have a theorem. So theorem is nothing but if Laplace f of t is equal to f bar s and L of g of t is equal to g bar s, then L of c1 f of t plus c2 g of t is equal to c1 Laplace of f of t plus c2 Laplace of g of t. This can also be written as c1 Laplace of f of t. In the starting of the topic, I have told you when Laplace is applied for the function of t, then you will get f bar s. There is nothing but a function f of t is transformed to function of s plus c2 g bar s, because we have here g of t. So when you apply Laplace to the function of t here, that transform to g of s, where c1 and c2 are constants, where c1 and c2 are constants. Now when you prove this, let us prove this the next page. Now here I am writing proof. Let us prove. Now here you know the definition of Laplace transform. So I am writing here by definition, here what is given, what we have to prove, Laplace of c1 f of t plus c2 g of t is equal to, now you know the definition of Laplace transform of f of t. L of f of t is equal to integral 0 to infinity e power minus st f of t dt. Now here this total term is considered as f of t. So we write here integral 0 to infinity e power minus st, and then here f of t is nothing but here c1 f of t plus c2 g of t, close the bracket, dt. This is by the definition. Then in the next step you write this is equal to integral 0 to infinity e power minus st into c1 f of t dt plus integral 0 to infinity e power minus st c2 g of t dt. Then after writing that, just you take out the constant outside, so that becomes c1 integral 0 to infinity e power minus st f of t dt plus c2 integral 0 to infinity e power minus st g of t dt. So in this step we are taking out the constants. So now after in the next step we can write c1, and this has become the definition of Laplace of f of t. So we write c1 Laplace of f of t plus c2 Laplace of g of t. So this is equal to c1 L of f of t is nothing but f bar s plus c2 L of g of t can be written as c2 g bar s. So hence proved. So this is the linearity property of Laplace transform. So this is, in this way we prove linearity property. Now let us have Laplace transform of some elementary functions. So let us know Laplace transform Laplace transform of elementary function. Now, so what are the elementary functions here are, we have k1 t power n e power at sin at cos at and so on. So let us find that one by one. Now first we take Laplace of k. Here Laplace of k is equal to k by s in bracket s greater than 0, where k is constant. Now how you get k by s? Let us see. Now for proving this, we want definition of Laplace transform. So the definition, you know, that is nothing but Laplace of f of t is nothing but integral 0 to infinity e power minus st f of t dt. So here the place of f of t, it is given k. So when you write the definition 0 to infinity e power minus st into, in the place of f of t we have to write k into dt. So this is equal to, now k is constant. So if you take out constant outside, then this becomes into k into integral 0 to infinity e power minus st dt. Then when you integrate e power minus t, then it becomes, you know, the formula of integral e power ax dx, that is nothing but integral e power ax dx is equal to e power ax by a. So we get k into e power ax. A is nothing but minus s, e power minus st upon minus s. Then when you apply the limits 0 to infinity, now in here we write k. Now I take this constant outside, this becomes minus k by s, and in bracket I apply the limits to t. So this becomes e power minus infinity, because when you put t is equal to infinity, this becomes minus s into infinity, that is infinity. So e power minus infinity minus e power 0. As you know, e power minus infinity equal to 0, this becomes minus k by s in bracket 0 minus 1. Here I write, since e power minus infinity equal to 0, e power 0 equal to 1. So when you take this, then when you multiply minus k by s with inside, you get Laplace of k is equal to minus k by s into 0, 0, minus into minus plus k by s into 1, k by s. So we get Laplace of k is equal to k by s. So in this way we prove next whatever elementary functions are there by using the definition of Laplace transform. Now let us prove for Laplace of 1. Second is Laplace of 1. So Laplace of 1 is equal to 1 by s, s greater than 0. So in the same way what we have done just now, we do the same. So here we take Laplace of 1 is equal to, the definition is nothing but integral 0 to infinity e power minus st into 1 dt. So now this can be written as integral 0 to infinity e power minus st into dt. This is equal to, now when you integrate, this becomes, you know, just now I have told you integral of e power ax is equal to e power ax by a. So we write e power minus st upon minus s. Then when you apply the limits here 0 to infinity, so this is equal to minus 1 by s I take outside, then in bracket, when you apply limit, this becomes e power minus infinity minus e power 0. So this is equal to, this is 1 by s in bracket e power minus infinity is 0 minus e power 0 is 1. So here when you multiply with minus 1 by s inside, you get 1 by s. So this is Laplace of 1. Now in the same way, when you go for a third problem, that is third elementary function, when you find that is Laplace of e power at. So let us find Laplace of e power at. So for finding that, again we take the definition of Laplace transform. So Laplace of f of e power at is equal to, now I apply the definition, integral 0 to infinity e power minus st into f of t is nothing but e power at. So I write e power at into dt. Then where here you can see bases are same. So when bases are same, then we have to add the powers. So when you add the powers, this is equal to integral of 0 to infinity e power. So when you add this, this becomes minus st plus at into dt. So this is equal to integral 0 to infinity. Now when you take common t, this becomes e power in bracket, you can write here a minus t, okay, e power a minus t, because here we take positive term first. So this becomes e power a into t is at, and minus s into t is minus st into dt. Now you integrate this. When you integrate this, then this becomes e power a minus s into t upon a minus s. As you know, just now we used the formula integral e power ax dx, that is e power ax by a. So that is nothing but we have written here. So after this, now we apply the limits here. Limits are 0 to infinity. Now when you apply limits to t, then this becomes e power a minus s into infinity upon a minus s minus e power a minus s into 0 upon a minus s. So as you know, this is equal to, you get e power infinity, e power. Now when you apply the limit here, so you can see a into infinity minus, here we are applying infinity to t here, so you get e power minus infinity minus e power 0 upon a minus s. So this is equal to e power minus infinity is 0 minus e power 0 is 1 upon a minus s. So now you can see this is equal to minus 1 upon a minus s. So now when you take in denominator minus common, then you can write s minus a, minus s minus into s minus s, minus of minus plus into a. So this is equal to, now you cancel 1, so that it becomes 1 upon s minus a. So this is nothing but Laplace of e power at. So Laplace of e power at is nothing but 1 upon s minus a. In the same way, now we find for the next. So here similarly we'll write here Laplace of e power minus at is equal to 1 upon s plus a. As you know, just now we have proved Laplace of e power at is equal to 1 by s minus a whereas Laplace of e power minus at is equal to 1 upon s plus a. You get 1 upon s plus a. So this is about Laplace of e power at and Laplace of e power minus at. Now we will go for next, that is fourth one, Laplace of sin at. Laplace of sin at is equal to, now we will find that is equal to a upon s square plus a square. Let us find this. Now as you know, when you are finding Laplace of sin at, we will write again by definition of Laplace transform. You know the definition of Laplace transform. Here f of t is given sin at. I am applying Laplace to sin at, so that becomes integral 0 to infinity e power minus st into sin at is nothing but f of t. So we write f of t is nothing but sin at dt. So as you know the formula, integral e power ax sin dx is equal to e power ax upon a square plus b square in bracket a sin bx minus b cos bx. Okay, this is the formula we use here. As you see here in this problem, a is nothing but minus s. The same way b is nothing but, you can see here x is nothing but t, so b will be what? A. So now when you substitute in the formula, now let us see what you get. Now this is equal to e power ax in the sense minus st, because x is nothing but t here in this problem. Okay, so now we write e power minus st upon a square is nothing but minus s whole square, so you get minus plus, so s square plus b is nothing but a, so you get a square. Okay, so then in bracket we write a is nothing but minus s, then sin b is nothing but a, x is nothing but t, minus b is nothing but again a, cos b is nothing but a, then x is t. Okay, so after this just close the bracket and apply the limit. Limit is nothing but integral 0 to infinity. Now when you apply 0 and infinity to t, so let us see what it becomes. Now I write e power minus s into infinity, so that becomes minus infinity upon s square plus a square in bracket minus sin minus s sin a into infinity, where we are substituting the place of t, so minus a cos a infinity, then close the bracket, then minus upper limit minus lower limit minus e power minus, that is nothing but 0 you get, because when you apply 0 to t to 0, so e power 0 upon s square plus a square, and then in bracket you get minus s sin 0 minus again a cos 0. Okay, so now we have applied upper limit minus lower limit. So after applying upper limit minus lower limit, as you know, e power minus infinity is 0. When you have e power minus infinity is 0, 0 into something is 0. So in the denominator we have to take common as 1 upon s square plus a square outside, and then we apply the limit. So this becomes, you get e power minus infinity into 0, then we write here 0, then here e power 0 is 1, then when you see here, you can see here we have sin 0 0. Okay, so then 0 minus, here you have cos 0 is 1, so here you get e power minus infinity, here you will get minus 1 by s square plus a square into, this is 0 minus a. So now this is equal to, now when you multiply with minus, so you get a upon s square plus a square. Now this is the answer for this. Okay, so in this way we do the problems based on elementary functions by using the definition of Laplace transform. So let us go for next problem. So that is Laplace of cos 80. Laplace of cos 80. Let us find Laplace of cos 80 now. This is a fifth one. Laplace of cos 80 is equal to s upon s square plus a square. Now for finding this, again we use the definition. By definition we write Laplace of cos 80 is equal to integral 0 to infinity e power minus st into cos 80, because f of t is cos 80 dt. So this is equal to, now again we have a definition, there is nothing but we have a formula, that is nothing but integral, since integral e power ax cos bx dx is equal to e power ax upon a square plus b square, and in bracket we can write a cos bx plus b sin bx. Now when you apply this, then here as I have told you just now, so a is nothing but here minus s, b is nothing but a. When you apply in the formula, you will get e power minus st upon s square plus a square, and in bracket you will get minus s cos at plus a sin at, and then close the bracket and apply the limit. Limits are 0 to infinity. Then when you apply the limits, so here it becomes e power minus infinity is 0, 0 into something is 0, and then when you apply lower limit you will get at last minus 1 upon s square plus a square in bracket minus s plus 0. So this is equal to s upon s square plus a square. So this is the answer for Laplace of cos 80. So in this way we prove the result. So hope you have understood here. So just now one of you have asked how you got minus 1 by s square plus a square. Here as you see, here this whole term has become 0. E power minus infinity is 0. 0 minus, here we have minus. So this minus 1 upon s square plus a square, and then here sin 0 is 0. Then cos 0 is 1. So this becomes 0 minus cos 0 1. So minus a. So this minus of minus, when you multiply inside you will get this one. In the same way here also we are doing the same, because when you apply infinity to here, the first term will become 0. E power minus infinity it becomes, so e power minus infinity is 0, and when you apply 0 to again in the place of t, so e power 0 it becomes. So upper limit minus lower limit, so 0 minus 1 upon s square plus a square, and then when you apply 0 to t here, so cos 0 is 1, so here you get minus s, and then when you apply 0 here, sin 0 is 0. So in this way you get, so Laplace of cos 80 is nothing but s upon s square plus a square. So in this way we do for Laplace of cos 80. Now when you go for next, that's nothing but Laplace of sin h80. So how you get Laplace of sin h80? Let us see. That is sixth one. Laplace of sin h80 is equal to a upon s square minus a square in bracket mod s greater than a. So here, as you know, the formula in hyperbolic, and one thing you remember, This whatever I'm doing here, the solutions of elementary functions will not be asked in the exam. For your convenience, I am doing this so that you can understand. If you forget, and in exam also you can do a side in rough and then you can apply in the problem. So in this way we have to do. So Laplace of sin hat, let us do Laplace of sin hat. Laplace of sin hat. For doing Laplace of sin hat, you have seen in your previous intermediate books, that is nothing but sin hat. This is nothing but hyperbolic function. So for doing hyperbolic function, you have to use the formula of hyperbolic, that is Laplace of sin hat is equal to, I have to take a Laplace of e power at minus e power minus at upon 2. As you know, sin h theta is equal to e power theta minus e power minus theta upon 2. I'll write here. So since Laplace of sin h theta is equal to e power theta minus e power minus theta upon 2, this is the hyperbolic function which you used in your intermediate. So here now this one I have used here in this problem. So when you apply this Laplace to this hyperbolic function, then this is equal to, I can write 1 upon 2, that is constant, Laplace of e power at. I'm separating the functions here by taking constant outside, minus 1 upon 2 Laplace of e power minus at. Now this is equal to 1 upon 2 into Laplace of e power at is nothing but 1 upon s minus a. You just now we have done, that is nothing but Laplace of e power at is 1 upon s minus a, minus again 1 upon 2. Now Laplace of e power minus at, just now I have written in the note, or similarly I have written, that is Laplace of e power minus at is nothing but 1 upon s plus a. Then after writing this, you can simplify this. Let us simplify the next paper. So when you simplify this, this is nothing but this is equal to 1 upon 2 in bracket 1 upon s minus a. I am taking 1 by 2 common, so that it becomes 1 by s minus a minus s plus a. So after writing this, now if you cross multiply this, this becomes 1 upon 2 in bracket s plus a minus s plus a upon yes. Here you can see you get LCM is nothing but s minus a into s plus a. Now this is equal to 1 upon 2 in bracket. Now you can cancel s, so that it becomes a plus a is 2a upon, now this is in the form of a minus b into a plus b, that is nothing but a square minus b square, that is s square minus a square. Now you get this one. Now you can cancel 2 upon 2 now, so that it becomes Laplace of sin hat. Laplace of sin hat is equal to s upon s square minus a square. Now so condition will be mod s greater than a. So in this way we prove Laplace of sin hat. Now let us prove next that is nothing but, I think seventh Laplace of cos hat. Laplace of cos hat is equal to s upon s square minus a square. So this is here a. So you can see here a upon s square minus a square, that is sin hat. For Laplace of cos hat you get in numerator s. Let us see how. Now solution for this is, you know, by definition of Laplace transform, Laplace of cos hat is equal to Laplace of, I am writing by hyperbolic, as cos h theta will be e power theta plus e power minus theta upon 2. So after this, now let us separate this by taking constant outside. So this is equal to 1 upon 2 Laplace of e power, so here in the place of theta we have 80, so we write 80, so here this is minus 80. So half Laplace of e power 80 plus half Laplace of e power minus 80. So after writing this, now you take 1 by 2 outside and then apply Laplace to both the functions. Then you get Laplace of e power 80 is nothing but 1 upon s minus a plus Laplace of e power minus 80 is nothing but 1 by s plus a. So then when you take the LCM and then if you cross multiply, then this becomes s plus a plus s minus a upon, now in the denominator you can see s minus a into s plus a, that becomes a square, a minus b into a plus b, so that becomes a square minus b square. So now this is equal to, now you can write this as 1 upon 2 in bracket, now a get cancels, you get 2s upon s square minus a square. Now this is equal to 1 upon 2, sorry, so you can cancel 2, so we can write Laplace of cos h at is equal to s upon s square minus a square. So in this way we do the problem based on Laplace of cos h at. So in this way prove, you can see we got s upon s square minus a square. So this is about Laplace of cos h at. Now let us go for next elementary function. So next elementary function is Laplace of t power n. Laplace of t power n is nothing but n factorial upon s power n plus 1, where n is a positive integer. In the previous class I have told you about positive integer and negative integer. Positive integer is nothing but which is greater than 0, and negative integer may be a negative integer is not a negative fraction, remember. Now for doing this here, this will be done in a separate way. So I mean we won't use any definition of Laplace transform here. We take first we take Laplace transform definition and then we take substitution directly. So let us write by definition of Laplace transform, Laplace of t power n is equal to, here we write integral 0 to infinity e power minus st into t power n dt. Now we take a substitution, put st is equal to x, implies we write, when you differentiate this, this becomes dt is equal to dx by x, dx by s. Here s dt is equal to dx, you get this s I take to other side, that becomes dx by x, dx by s. Then when you apply to Laplace of t power n, here when you substitute this in this definition, integral 0 to infinity e power, in the place of st we write x minus x into t is nothing but, from this we can take t is equal to x by s, so I can write this as x by s whole power n, into the place of dt I can write dx by s. Okay, so then after that this is equal to, you can write I take here you can see x by s whole power n we have, here s we have, so if you take outside you can write this as s power n plus 1, because bases same, power should be added, so that becomes 1 upon s power n plus 1 integral 0 to infinity e power minus x into, here you can see x power n we have, let us write x power n first and then write dx. Then after writing that, this is equal to 1 upon s power n plus 1 integral 0 to infinity e power minus x into x power, here I add and subtract with 1, so that it becomes the definition of gamma function. So Now this is equal to 1 upon s power n plus 1 integral 0 to, okay, we have already taken. So let us just cancel this. Now here I can get only this is equal to, in the place of this, as you know the definition of gamma function, that is integral 0 to infinity e power minus x power n minus 1 dx. So here in the place of n we have n plus 1. So I can write gamma n plus 1 upon s power n plus 1. So as you know here it is given where n is a positive integer. So first we write Laplace of t power n. What you got just now? First gamma n plus 1 upon s power n plus 1. We got this. Then here in the starting we have given Laplace of t power n is equal to n factorial upon s power n plus 1, where n is a positive integer. So we have to write, if n is positive integer, if n is positive integer, we have a condition, then we write, then gamma n plus 1 is equal to n factorial. I have told you before when we are doing problems based on gamma function. So in the place of gamma n plus 1 we have to write n factorial. So Laplace of t power n is equal to n factorial upon s power n plus 1. So in this way we do the problem when a problem is given in terms of gamma function. So in this way we find L of t power n. So let us go for next. So these elementary functions are enough for doing the problems. Whatever problems will be given, let us do that. So now I'm doing the problems based on the example. I'm showing you the example based on piecewise continuous now. So as I have told you, existence of in the when I have started the topic sufficient conditions for the existence of Laplace transforms of a function, we have two conditions. First condition is nothing but piecewise continuous function. Second one is function of exponential order. Okay, so let us do a problem based on piecewise continuous or sectionally continuous function. Okay, so let us do problem based on piecewise continuous. I am showing you the example for that. Okay, so let us do that. Find the Laplace transform of f of t is equal to sin t 0. So here sin t comma 0 less than t less than pi. So this is the interval in which the function f of t lies, and 0 t is greater than pi. So just before doing this problem, what we have completed, first we have completed the definition of Laplace transform. Laplace transform is nothing but Laplace of f of t is equal to integral 0 to infinity e power minus st f of t dt. As you know, as I have told you, a function of t will be given when applying Laplace, that is Laplace transform operator L. We will change function of t in terms of function of s. Okay, so then we have written how we do inverse Laplace transform, and as I have told you, L inverse is nothing but inverse Laplace transform operator, that we will study in the next coming topics. And then we have started sufficient conditions for the existence of Laplace transform. How will be the problem of Laplace transform, what are the conditions, how we will solve that, I have shown you that we have, as I have told you, we have two conditions. First condition is the problem will be in terms of piecewise continuous. Second condition is the problem will be in the form of exponential order, that I am showing you the example right now. And then after that we have completed linearity property. In linearity property I have told you Laplace of c1 f of t plus c2 g of t is equal to C1 L of f of t plus C2 L of g of t, that is equal to C1 f bar s plus C2 g bar s. That is nothing but linearity property. When a constants are given in the problem or with a function of t, then we have to separate how we separate that constant outside. We have shown by using linearity property. And then we have done, so we have as I have shown you how to find uh, Laplace transform of elementary functions. So we have solved Laplace transform for the elementary functions. What are the elementary functions we have done here? K1 e power at, e power minus at, sin at, cos at, sin h at, cos h at, t power n also. So these are all very useful, and this will be used in the coming problems. So basically, as I have told you, why we use Laplace transform, why we are studying Laplace transform is nothing but in order to solve linear differential equations. In the previous units, that is third unit and second unit, we have studied about linear differential equations we have studied. In that we have studied how to find complementary function and particular integral. So instead of finding all that, so Laplace transform is used, is a very useful tool where we can directly solve linear differential equations in coming topics. Okay, so without finding complementary function and particular integral. So let us have an example of Laplace transform when a piecewise continuous function is given. So here this is the function. What is the function given? Function of t is given sin t in the interval 0 less than t less than pi. So there, as I have told you in the definition, there will be an interval from a to b, or closed interval be given a comma b. So here what are the endpoints here? 0 and pi. So here for a function 0 t greater than pi, here from that is nothing but from pi to infinity. So what are the intervals here given? 0 to 0 comma pi and pi comma infinity. So this is nothing but the intervals. Now when you apply the by definition of Laplace transform, let us solve this problem. Laplace of f of t is equal to integral 0 to infinity, I am writing the definition first, minus st f of t dt. This is the definition. So when you apply in this definition, so this is equal to, you can write this as integral 0 to, as I have told you, 0 to pi, pi to infinity. So 0 to pi, if you take the interval, then e power minus st, what is the function here? Sin t. So we write f of t is nothing but sin t dt plus integral. Now in the next interval it is given from pi to infinity, so we write pi to infinity e power minus st. In this interval f of t is 0, so we write 0 dt. After writing that, now the next step we can see here, e power minus st into 0 is 0. So only the term remained is integral 0 to pi e power minus st sin t dt. Then we have just now we have used the formula, that is nothing but since integral e power ax sin bx dx is equal to e power ax upon a square plus b square into a sin bx minus b cos bx. This is the formula we have used in the previous for finding the elementary function. So now this we use here in this, this is the, if you put in bracket, now in this problem, now a is equal to what we have? Minus s. Okay, then b is equal to what we have? 1. Okay, then what is x here? X is nothing but t. Now when you apply in the formula, this is equal to e power a is nothing but minus s into t upon a square plus b square. A is nothing but s square plus b is nothing but 1 square is 1. A square here minus s will be there, the minus of minus plus s into s square. So then we have here, if you apply in this formula, so minus s sine t, because b is 1, minus b is 1 cos b is nothing but 1, x is nothing but t. So in this way you get. Now after writing in the formula, we apply the limits. What are the limits here? 0 to pi. So after this, when you apply the limits to t, then by putting 1 by s square plus 1 as common, then in the bracket, so when you put pi to t, so this becomes e power minus s pi, in bracket we write minus s sine pi, okay, then minus cos pi. This is over, this is upper limit, minus lower limit. So lower limit is we are applying 0 to t, so this becomes e power 0, in bracket you get minus s sine 0 minus cos 0. So after writing that, close the bracket. Now in the next step you get this is equal to 1 upon s square plus 1, and in bracket you get e power minus s pi in bracket sin pi is 0. So you get 0 minus cos pi is minus 1. So close the bracket, and then minus e power 0 is 1, then sin 0 is 0, then cos 0 is 1. So after writing this, now when you simplify this, you can get e power minus s pi into 0, 0, e power minus s pi, this minus of minus plus 1. So we write the conclusion e power minus s pi upon s square plus 1. So this is the answer for the given problem. So this is about for piecewise continuous. I'll show you one problem based on exponential order. So that is nothing but we have a problem that is prove that the Laplace transform of e power t cube does not exist. So this will be the problem. So now when you write the solution, now here it is given f of t is given e power t cube. Then as I have showed you the formula is nothing but limit t tends to infinity e power minus at f of t is equal to, I can write limit t tends to infinity e power minus at into f of t is t cube, e power t cube. So now this is equal to, I can write limit t tends to infinity, bases are same, power should be added. So if you add the powers, you get e power t cube minus at. Now when you apply infinity to t, so you get infinity. E power infinity is infinity. So we write f of t is equal to t cube e power t cube. F of t is equal to t cube e power t cube is not of exponential order, full stop. Hence its Laplace transform does not exist. So in this way we do the problems based on piecewise continuous as well as problems based on exponential order. So when you do the problems based on elementary functions, in the previous, if you do one problem, So let us do one problem based on elementary function. So problem will be find the Laplace transform of t square plus 1 whole square. As you know, here f of t is given as t square plus 1 whole square. If you expand this, you get t power 4 plus 1 plus 2t square. Now when you apply Laplace transform for the function given, then this becomes Laplace of t power 4 plus Laplace of 1 plus 2 into Laplace of t square we can write. So after writing this, when you apply Laplace to t power 4, that becomes 4 factorial upon s power 5. As you know the formula, Laplace of t power n is equal to n factorial by s power n plus 1. As you know, here 4 is greater than 0, that is a positive integer. Then plus Laplace of 1 is nothing but 1 by s plus 2 into, again Laplace of t square is nothing but, here 2 is nothing but a positive integer and greater than 0. So we can write n factorial, that is nothing but 2 factorial upon s power n plus 1, s power 2 plus 1 is s cube. In this way, we complete by taking 4 factorial is nothing but 4 into 3 into 2 into 1, that is 24 upon s power 5 plus 1 upon s plus 2 into 1, 2 into 2, 4 upon s cube. So this is nothing but Laplace of t square plus 1 whole square. So this is nothing but finding Laplace transform when by using elementary function. Now when you do another problem, let us do second problem. Second problem is Laplace of 5 sine t plus 2 sine 3t. If it is given, then how to apply Laplace transform? So here you can see this is given 5 sine t. So in the solution we write first f of t. F of t is equal to 5 sine t plus 2 sine 3t. Now when you apply Laplace transform to f of t, then by using linearity property, taking constants outside, we write 5 Laplace of sine t plus 2 Laplace sine 3t. Then when you apply the formula, that is nothing but Laplace of sine at is nothing but a upon s square plus a square. A is nothing but 1 here, so I can write 5 into 1 upon s square plus 1 plus 2 into, again this is nothing but Laplace of sine at. As I have told you, Laplace of sine at is nothing but a upon s square plus a square. So 2 into 3 upon s square plus 3 square. So at last we can write this as 5 upon s square plus 1 plus 6 upon s square plus 9. So in this way we do problems based on elementary functions. With this we wind up today's class. Thank you for joining.